This is the luckiest maths teacher in the world. Thank you so much for tuning into this video on similar figures. So last time we went through congruent figures. That's when I take a shape and I say translate, rotate, or reflect it. I get another shape that's the same size and same shape. Well, similarity, we do perform those transformations of translation, reflection, or rotation, but we also perform an enlargement or a reduction. So if I take this shape and I reduce it to a smaller version of itself, these two shapes on screen are similar. Also, I could have taken my original shape and enlarged it. I could even rotate it a little bit. So if the translation, reflection, or rotation is accompanied by an enlargement or a reduction, then the two shapes are similar. So all three shapes on your screen are similar. But let's go through a more definitive way to tell whether or not two shapes are similar. Basically, two shapes are said to be similar if they are the same shape but not necessarily the same size. So they can't just both be like triangles, they both have to be like equilateral triangles or whatever. So more formally, two shapes are said to be similar if they are equiangular, so that means that pairs of corresponding angles are equal, and also pairs of corresponding sides are in the same proportion. Note, for two shapes to be similar, they have to satisfy both of these two conditions. And it's very important you understand that, because it's possible that two shapes will satisfy one but not the other of those conditions. And we're about to look at examples of these, so please pause and copy down this definition if you need. So let's go through each of these pairs of shapes and determine whether or not they are similar. So we'll start up here with the red shapes. So even if I tell you that these are both rectangles, these two shapes are not similar. So rectangle would imply that all the angles are equal to 90 degrees. So these two shapes are actually equiangular. Pairs of corresponding angles are equal. They both have the same set of angles. The reason that they are not similar is the sides are not in proportion. So 12 over 6, the largest side of the first one divided the largest side of the second one, is not equal to 8 over 3. So they're not in proportion. I would have to times 6 by 2. I would have to double the length of the longer side, but I'd have to more than double the length of the shorter side. I need to actually times by 2.6 recurring. Now, you don't need to write what's in blue. You just need to know the sides are not in proportion, so these are not similar shapes. So in the second one, note the long side is double the length of the shorter side, but that's not true in the first shape. So that's why, even though these are both rectangles, they are not considered similar shapes, because sides are not in proportion. So let's look at the second two shapes. So the first one's like a rhombus. So that's a type of parallelogram. And the second shape looks more like a square. So our intuition should be that these shapes are not similar. One looks more like a square, the other doesn't. Now, that's not enough to say that they're definitely not similar. You need to use a better reason than that, but that's just some intuition. So if I tell you the second one is a square, it will also have all of its angles equal to 90 degrees. But the first shape doesn't necessarily have that. So for the green shapes, even though the sides are in proportion, because 6 over 3 is 2, for each side of the smaller shape, you times it by 2 to get the side length of its corresponding side in the largest shape of 6. So sides are in proportion, but angles are not equal. So this angle here and this angle here are going to be equal, but we're not told they're right angles. Same with those two angles there. So the first shapes were not similar because the sides were not in proportion even though the angles were equal. For the second pair of shapes, they are not similar because the opposite, even though sides are in proportion, the angles aren't equal. They're not equiangular. So let's look at the third set of shapes. So I'm telling you that they are both squares. So that means both of them have all angles equal to 90 degrees. Now it turns out whenever you have any two regular shapes, as long as they've got the same number of sides, they will be similar. So these two shapes are similar. So they have basically what the first two shapes had. So they have all angles equal, pairs of corresponding angles are equal. Both of them have 4 90-degree angles. Sides are in proportion to, because 15 over 10 is 1.5. In other words, every side in the larger shape is 1.5 times as long as its corresponding side in the smaller shape. I could change the 15 with any other number and these shapes would still be similar. That number divided by that number would give me the same answer regardless of which sides I chose in the respective shapes. So any two squares will always be similar to each other. Any two regular pentagons, so 5-sided shapes with all sides equal and all angles equal, they will always be similar too. Any two regular shapes with the same number of sides are always similar because they will always have the same set of angles and sides in proportion. So now what we're going to do is look at how to construct some similar shapes when given a center of enlargement. So what we are going to do here is take the triangle ABC and enlarge it by a scale factor of 2 about the point O, which is called the center of enlargement. So we're going to end up creating a shape that is similar to the shape ABC. Now the scale factor is the number I multiply by each side of the smaller shape to get each side in the larger shape. So what that means for our question here, we're going to end up enlarging by a factor of 2, a scale factor of 2. So our triangle is going to have sides that are twice as long as our original triangle. So think of it like this. O is like a fixed point, and we're going to stretch this shape in the direction away from O, the direction towards the triangle, and create a shape that is basically twice as big. Its angles will be the same, but its sides will be twice as long. So this is how we do it. What we do is we measure the distance from the center of enlargement to each vertex of the shape. So I've measured the distance here in centimeters. Obviously, it might be different on your screen. Your screen won't be the same size as my iPad, but you should get a very similar answer. So now what I have to do is I have to double the distance. I'm going to move each of these vertices so it's twice as far away from the center of enlargement, but on the same line. So let's start with A. So it was 4 centimeters on my screen from the center of enlargement. I've got to now move it so it's 8 centimeters away, but on the same line. So the distance is now going to be 8. So it was 4 from O to here. That was 4. So this distance here will be another 4. So the total distance is 8. So I'm going to move A to there. Similarly, I'm going to move C to here. So that this distance here is another 2. And B is going to move about here. So that the distance is on the same line but double. This is another 4. The total distance is 8. So what we do is we label the new point where A goes as A dash, B dash for where B goes, and C dash for where C goes. And then we just join up those vertices and we have a triangle like this. Mine's not perfect. Of course, yours will be better using a ruler and not having to contend with an iPad. But now these two shapes are similar. The scale factor is 2, so each side length in the larger shape is double its corresponding side in the smaller shape. All right, now we're going to use similarity to find unknown sides. Looking at these two pairs of shapes, I'm telling you that they are similar, and we're going to find the value of the unknown pronumerals. So I've set up the top there, the scale factor. To calculate that, you take a side in the larger shape and divide it by its corresponding side in the smaller shape. So you should always get a number greater than or equal to 1. If you do it like this, if you calculate the scale factor the way I said, you can use this rule here. If you're going from the smaller shape to the larger shape, you times by the scale factor, and if going from the larger shape to the smaller shape, you divide by the scale factor. So let's look at the 2 red triangles up here. So we're looking up here. So the scale factor is the larger shape divided by its corresponding side in the smaller shape. So 9 and 6 correspond because that is the side that hits the green and the yellow angle. So 9 over 6 is just 1.5. That's the scale factor. That's saying that the sides in the larger shape are 1.5 times their corresponding sides in the smaller shape. So x is in the larger shape here. So we times by the scale factor. We take the side in the smaller shape times by the scale factor. X is 8 times 1.5 or 12 units. So let's now look at the bottom shape. So here we're finding an unknown in the smaller shape. So note that the second shape, much bigger than the first, has also been reflected. So we have to make sure we get our bearings right. So y is the side that touches just angle with one arc. So y will correspond to 25. Now to look at the other sides on which they correspond to, you could also note y and the 25 are the longest side. 8 and 20 are like the second longest side, the ones opposite the longest side, and 6 and 15 also correspond. Two sides, the diagonal side that doesn't touch either of the angles with the arc on it. So whichever way you want to calculate it, the scale factor is larger divided by smaller, larger divided by smaller. In cases you get the number 2.5. If we didn't, we would have done something wrong because we were told that these shapes were similar, meaning all sides need to be in the same proportion. So now when we're finding y, we take its corresponding side in the largest shape and we divide by the scale factor, because our rule up here, if I'm going from the larger to the smaller, so I started with the larger and I'm going to its corresponding side in the smaller shape, I divide by the scale factor, so I just get 10. All right, now we're just going to do one question that's a little harder to calculate the pre-numeral. So these two triangles I'm telling you are similar. So we need to find the value of x. What makes this harder is that x is in more than one spot. But what we can do is set up an equation to solve x. So here we can't calculate the scale factor directly because we don't have the lengths of two pairs of corresponding sides. But what we know is that sides are in proportion. So this side and this side correspond to each other. They're both the sides touching the blue and the red angle. So 27 divided by x, that'll actually be the scale factor. That is going to be the same as this side divided by its corresponding side. Now we have an equation that we can solve. What we do is we times each side by x to get rid of the x on the bottom of the fraction. So I get 27 equals x squared divided by 3. Now I want to times by 3 to get rid of this fraction. So I get 81 equals x squared. And of course, x is just the square root of 81, which is equal to 9. And we can easily check if we're right. This makes sense because 27 over 9 means this side is 3 times as long as that side, and it means this side is 3 times as long as that side. So we know we've done something right. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.